So, one of the things we said we can attempt when solving CSPs, when we want to fight this combinatorial explosion, is to pre-process the constraint network before we attempt looking for a solution. And the simplest form of pre-processing that we can do is to ensure that the network is R consistent. So, let us look at that and see what is R consistency and how to enforce that. So, let x y be an edge in the constraint graph. Remember that the constraint graph tells you which variable is related to which other variable, and x y is an edge which says x and y they participate in a constraint in the network R. Now, a variable x, which is one end of the edge, is said to be R consistent with the other variable y if for every value a belonging to its domain d of x, if for every value a in d of x there is a value b in d of y. If that is the case, then if you were doing a search algorithm, intuitively that is the meaning of that, that if you were to assign a value of a for variable x, then you would find a value b for a variable y which is related to that, and that is what we mean by R consistent, that x is R consistent with respect to y if for any value you choose for x, you will find a value for variable y essentially from its domain obviously, and that value means that pair A B must belong to the relation R x y that we are talking about. X can be made R consistent with respect to y by this algorithm which is called revise. It is a simple algorithm. It says I am going to make this variable x R consistent with the variable y, and what do? You look at every value a in the domain of x. If there is no value b in the domain of y such that this condition is true, which means that they can be assigned together or that they belong to the relation R x y. If you cannot find this value y, you simply delete a from d of x. So, to make a variable x are consistent with respect to y, you delete those values from its domain for which you cannot find a value in y, and that is a simple algorithm. It is called revise, and the complexity of this algorithm is going to be order of k square, where k is the size of each domain, because essentially you are searching through both the domains. For every value in x, then you are looking for a value in y. So, at most you can have k square kind of this thing, I mean, and that would happen when that variable is not, it cannot be, it is not R consistent with that, you would have exhausted all values. We say that an edge x y is said to be R consistent if both x and y are R consistent with respect to each other. So, x is R consistent with y and y is R consistent with respect to x, which means that for you choose a value for x, you will always be able to choose a value for y, and vice versa. If you choose a value for y, you will always be able to choose a value for x. What do we mean by you will be able to choose a value which satisfies the constraints that are expressed in the constraint satisfaction problem? And an edge can be made R consistent. First you call revise x with respect to y, and then you call revise y with respect to x, then the edge itself will become R consistent. A network R is said to be R consistent if all its edges are R consistent. And what do we mean by all the edges? That all the edges in the constraint graph. So, we want R consistent networks, because we can see that we may have to do less backtracking if a network is R consistent, because for every variable at least we know that for the next variable we can find a value. So, a network is R consistent if all its edges are consistent. So, the question we want to ask is, will a cycle of revise calls over all edges? So, we know what this revise does, right? In both directions do the trick. So, the question we are asking is, if for each edge x and y we make it arc consistent locally, which means we call revise x with respect to y and we call revise with respect to x, and we do this for each edge, will it make the network arc consistent? So, remember that we say an edge is arc consistent if for every value of x you can find a value in y, and for every value of y we can find a value in x. And we saw that we can do this by calling revise x y and then calling revise y x. But we also said that a network is arc consistent if all its edges are arc consistent. The question is, what is happening if you think of what is happening in the revise algorithm is that you are pruning the domain of, when you are calling revise x with y, you are pruning, or you are possibly pruning domain of x, because you will remove values of x which are not, for which you can't find a value of y. So, can this have a cascading effect is the question we are asking, or is it enough to call revise once for every edge? So, as I said, the effect of revise x y is to prune the domain of x, and can a disappearing value from the domain of a variable at the end of an edge, so variables are always at the end of edge, affect the arc consistency of some other edge? If you are going to remove some value from d of x, will it affect some other arc consistency? And we can show that from an example that this is indeed the case. So, let us look at this very small example. In which there are 4 variables, and this is a matching diagram for this particular thing. And you can see that nodes which are colored black are consistent with their neighbors essentially. In the sense, if you look at dx, then the first 2 nodes and the last node, they have a corresponding value in dy. That is, we have colored them y. This variable, this value in x does not have a corresponding value in y. So, when we call revise x with respect to y, this value will be pruned away essentially. Likewise, there are a couple of more values. Some nodes we have colored in gray. So, for example, this node in dz, it has a value in dy, but it does not have a value in dw essentially. So, if you do one cycle of calls, what does one cycle of call means? You call x with respect to y, y with respect to x, and this is a constraint diagram. X is related to y, y is related to z, and z is related to w. The others are not related to each other. So, in one call you will call revise x with y, y with x, then y with z, z with y, and then z with w and w with z. So, this would be a cycle of one call, 6 calls to revise. These are the 6 calls: x with y, y with x, y with z, z with y, z with w, and y with z essentially. If we do that, then if you work out this example yourself in this particular order, if you call the revise module, then the resulting constraint graph will look like this as shown below. And now you can see what has happened is that when this value in z when we call revise z with w, this value did not have a value in w. So, this value got deleted from here. So, it is no longer here, as you can see, which means this value does not have a supporting value in dz essentially. So, after this cycle of calls, dy is, y is not arc consistent with respect to z, because there is a value in y dy which does not have a corresponding value in dz. In fact, there are 2 such nodes in dy. So, those also must be removed essentially. So, supposing you remove this, then what happens to this one essentially? So, there is some cascading effect. So, the simple algorithm which says that I will call revise twice for every edge and be done with it will not work. So, that gives us a clue to the simplest of algorithms for doing making a network arc consistent. it is called AC1. It cycles through all edges as long as even one domain value changes. So, it is a little bit of a brute force this thing, but it works. It is correct in the sense that it will give you a network which is arc consistent. What does it do? It goes into a cycle which we have shown in the repeat loop, and which says that for each edge x y make these two calls to revise in the constraint graph. And how often do you repeat this? Till no domain changes in the cycle. If there is no domain change, then there is no question of propagating that effect essentially. So, it is a little bit of a brute force effort this thing, but it works, and that is the first simple algorithm that we have looked at. If there are n variables in the network and each has a domain of size k, and if there are e edges in the constraint graph, then because you are iterating over that, every cycle has a complexity of e k square. Why? Because revise has a complexity of k square, and therefore, every cycle will have a complexity of e k square. Now, in the worst case, and you can try to construct a network which is like that. In the worst case, the network is not arc consistent at all essentially, and in the end you end up removing one value in the worst case, one value in every cycle from some domain essentially. So, in the end you will end up removing all values, but the number of cycles that it will take will be pretty large, and that is n into k cycles. And why is it n to k? Because there are n variables and each variable has k values, and if you want to remove them one by one in every cycle, so you will get need n into k cycles. That combined with the fact that each cycle has complexity e k square gives you the complexity of AC1, the worst case complexity as n e k cube essentially. This is the worst case complexity. In the best case, the network that you are given itself will be arc consistent, and in the first cycle itself there would be no change essentially. So, this is the worst case complexity. So, this is an example that we had seen earlier, a very simple object here along with the constraint network, and if we apply this algorithm here, then you would see that only the vertex labels which are shown in black will remain and the others will vanish. So, again maybe I should ask you to do this as an exercise, but just to understand what is happening here, if you look at this vertex V4 which is in the middle of this diagram here, you can see that in an arc consistent network it can either be plus plus plus, which means it is a convex object, or it can be minus minus minus, which means it is a concave edge, but the other combinations would be removed because they are not consistent with each other, and arc consistency would reduce the network to the one which is shown in black here essentially. This is a recap of this thing, the posing of the n-queens problem as a binary constraint network, and the question I want to leave you with is to think about that, is this networks as given as defined here, are they arc consistent or not essentially. Here is a map coloring problem. We saw that there are two solutions in this problem we saw, and this is a network as given to us. So, of course, we tried this dynamic variable ordering algorithm earlier, but let us see what happens when we apply this AC1 algorithm to this network before we start searching essentially. So, remember that this consistency algorithms can be applied as a pre-processing phase, and supposing we were to do that, what would happen here. So, this is a constraint graph on the left, and we are going to remember cycle over the edges. For every edge we are going to call revise twice, and what will happen is that something would get deleted from some domain. So, for example, when we call revise d with respect to E, then this value of r in d will get removed, because we can't find a corresponding value in E. E has to be something other than R. So, D cannot have the value R essentially. So, that is gone. Then let us say when we call device with respect to C, this value blue must go, because C has only one value, which is blue. So, if you were to choose blue for D, we will not be able to choose a value for C. So, B must go from here. Then if you call revise B with respect to C, again the same thing, blue must go from here, because we can't find a value in C essentially. Then we call revise B with respect to D. Now, D has got only one value left, which is green, and if you were to choose green for blue, then we would not find a value for D. So, we must remove D from the G from the domain of B essentially. And at this point, the network has become arc consistent, and it so turns out that for some problems, and this happens to be one of them, for some networks, arc consistency results in backtrack-free search. What do you mean by backtrack-free search? You take the variables in any order and you pick a value for them, go to the next variable and so on, and you will end up with a solution. And you can see that in this problem that is the case essentially. Let us say you start with A, and then you either you choose B or you choose green, the other values will come without having the need to backtrack. Now, this is again to re-emphasize the fact that there is a relation between logical reasoning and consistency enforcement essentially. Now, if you look at the knowledge base on the top, which is a proportional knowledge base, which has got 4 statements. One says that P is true, then the second statement says that P implies Q, the third statement says Q implies R and R implies S. So, even if you look at this very intuitively, you can see that from this you can, from P, and if you remember your modus ponens, you know that from P and from P implies Q, you can conclude Q. Now, once you have Q, then from Q and Q implies R, you can conclude R, and once you have R, then from R and R implies S, you can conclude S. So, you can conclude that P is true, Q is true, R is true and S is true, given this knowledge base essentially. Now, if you look at the constraint diagram, so if you remember, we had mentioned that this is how the constraint diagram for the implication looks when we have Q and R. Remember that there were 3 rows in the truth table for which Q implies R can be true. Those 3 rows are captured by the 3 edges between the variables Q and R. If Q is true, R must be true. If Q is false, R can be either true or R can be false essentially. These were the 3 rows when Q implies R is true. So, the knowledge base that we have can be represented as a constraint satisfaction problem, and this is a matching diagram for the problem as given to us. Why does P have only true in it? That is because we have said that P is equal to true. So, we have already put in a constraint that P cannot have a value false essentially. But the other values we still do not know. We have not made the inference, we have not used modus ponens to say that Q must be true. We have said that this is a knowledge base given to us essentially, and instead of using the logical reasoning process of modus ponens, we say let us do consistency enforcement here. So, supposing we do arc consistency here. Now, if you look at this diagram, remember that you want to, so let us say we call revise Q with respect to P. What will happen? That you look at all the nodes in Q and see if there is a corresponding value in P or not. So, if you revise P with respect to Q, no change will happen, because there is only one value in P and that has a matching value in Q. But when you do revise with Q with respect to P, then it is fine, this value T has a matching value in P, but this value does not have a matching value in P. So, that will get managed. So, if you just continue this process of making it R consistent, you will end up with a network in which all the conclusions that you could logically draw are present in the network, that P is true, Q is true, R is true and S is true. Now, we have looked at this R consistency and we have looked at this notion of enforcing R consistency with this algorithm called AC1, which we mentioned was a brute force approach. Next, when we meet, we will look at this idea of propagation or constraint propagation, as some people say, and we will devise a much more efficient algorithm for achieving R consistency, and we will do that in the next session.